Hey everyone, it's Bradley Bush again with another algebra video. Today we're talking about vertical asymptotes. What in the world are those, right? What a weird name. First off, we'll talk about a review of rational functions because we find vertical asymptotes in rational functions. Second, we'll define vertical asymptotes so you know what they are. Then we'll teach you how to find them. And then we'll give you a worked example. I'll also put the timestamps for these in the video description so that you can skip ahead if you want. Rational function is just a fraction with polynomials in the numerator and denominator. So a rational function f would have some polynomial in the top and some polynomial in the bottom of the fraction. That's it. And the domain would be everything except those x values that made the polynomial in the denominator equal to 0. Asymptote. That is a pretty weird word, right? An asymptote is an invisible line that gets closer and closer to the graph of a curve without touching the curve as x approaches infinity or negative infinity. So as x gets bigger or smaller, or as x approaches a specific value, like a, an asymptote will kind of like draw the curve to it. The curve and the asymptote will get closer and closer and closer. It's the curve that's moving, and the asymptote stays solid and fixed. But you don't ever see the asymptote because it's invisible. But it kind of governs the behavior of a function. There are three types. There's the horizontal, the vertical asymptote, and the oblique or the slant asymptote. And two common types of rational functions. One is the reciprocal function, y equals 1 over x. Kind of looks like it has two bow and arrows that are facing each other, both maybe shooting an arrow to the origin. The first one is in the top right quadrant, or the quadrant 1, and the second one is in the third quadrant, or the bottom left quadrant. And they're both these bowed looking shapes that are the angle of the bow is pointing towards the origin. And they have asymptotes on the x and y axis, so they never actually touch those x and y axes. The second one, common function, is 1 over x squared. And it looks kind of like the function 1 over x, the reciprocal function. In the top right, it has that bow and arrow looking shape. But the one that used to be in the bottom left is now in the top left. So it's kind of flipped up, so both of them are positive. So it kind of looks like the Atari symbol if you're old enough to know what that looks like. And then here's just a bunch of information about the two common functions that you can pause the video now and just check out. Here's some examples of the rational functions. They can take on kind of interesting shapes. You can have U shapes, you can have L shapes, you can have elongated S shapes. You can even have slant asymptotes that kind of give you two really, really angled shapes with the tips of the angles facing each other. Let's talk about arrow notation. Arrow notation is used in the definition of asymptotes, so it's kind of important to understand it. And you will see the arrow notation also in calculus if you go on to calculus. So our first symbol is the symbol x, and then there's that little arrow, right arrow, and then there's an a with a plus in the power. So that is read, x approaches a from the right. If you have a and then the right arrow, and then, sorry, if you had x and then the right arrow, and then a with a minus sign in the power, then that means x approaches a from the left. And to kind of give you a better understanding of what I'm talking about, I'm going to draw a little xy curve plane here. And I'm going to have some function that is moving along here. And I just do it kind of like an S-shaped, elongated S-shaped. So say we have some x value. Say that x value is, we'll call it A. And A happens to also be 3. So if I was approaching A, or 3, from the right, then I would be coming from above to the right of A. So I would be out here. Maybe I should make that a little bit bigger, right? Let's make this x-axis a little bit larger so you can actually see what I'm talking about. So we would start, if we were coming towards A, say we're going to say x is approaching A from the right side. So we'd have x, right arrow A with a positive in the power. Then we would start at, like, I don't know, x equals 7, and then we'd go down to 6, then we'd go down to 5. So we would keep going closer and closer and closer to taking successively smaller x values until we got really close to A, but we actually didn't hit it. We got super, super close. So we would be approaching A from the top, from the right side, from the positive side. So that's all it means. You're just taking successively closer values to A from either above A or below A. So how about this next idea where we have x and then right arrow and then infinity? That just means as x approaches infinity, or in other words, x gets bigger without bound. We also can have x approaching negative infinity. So x, right arrow, then negative infinity. That means x gets smaller and smaller, never stops getting smaller. Here's our definition of a vertical asymptote. So a line, a vertical line, x equals A, is a vertical asymptote if the following scenarios happen. So as x approaches A from the right, the function gets closer and closer to infinity, or goes to infinity, or goes big and never stops. So if we have some vertical asymptote, which I have here as a dashed line, vertical line at A, as I'm moving to the left, I'm getting closer to A from above, you can see the function is shooting up to positive infinity. If that happens, you have a vertical asymptote at x equals A. Same thing, but if you come from the left of the vertical asymptote A, x equals A, if your function is coming from the left, but as you get closer to A, the function shoots up to positive infinity, then you have a vertical asymptote. The same scenario can happen, but your function could shoot down as you got closer to A from the left or the right and go to negative infinity. If either of those cases happen, then you have a vertical asymptote at x equals A. And A, again, is just a number like 2 or 5, negative 10, some number on the x-axis. How do I find vertical asymptotes? Well, if our function f is a polynomial divided by a polynomial, or a rational function, then it's actually super easy. We first make sure that the polynomial on the top and the bottom are simplified and don't have any common fractions. I shouldn't have said fractions there. What I really meant to say was common factors. The polynomial on the top and the bottom cannot have any common factors. And then we just take the polynomial on the bottom, set it equal to 0, and we solve that equation. That will give us some x values, and those x values are our vertical asymptotes. And that's it. Just a note, though, you may find that there are some common factors in the top and the bottom when you're given a rational function. And you might think, well, aren't those asymptotes the ones in the bottom? Well, no, because if you have common factors, so say I have polynomial P1 in the top and polynomial P2 in the bottom of my rational function, and then I have this common factor x minus c in the top and in the bottom. Really, that common factor is going to cancel out and go away. And then you'll go back and look for vertical asymptotes. But there's something interesting about that common factor, though, x minus c. If you set it equal to 0 and solve, you get x equals c. And x equals c, at x equals c, you actually have a hole in your graph. So what happens is your graph is coming along somewhere, right? Just drawing in the old graph. And at some point, you have a hole. So what happens is there's actually a break in your graph. So let me draw that a little bit better. So it comes up, there's a hole, and then it keeps going. So it's literally like someone just took a pinhole out of your curve, and that pinhole happens at the value x equals a, or sorry, c, whatever the constant is in that common factor. Kind of cool, huh? All right, let's look at an example of vertical asymptotes. How do we find them? How does it work? So we just decided how we find them. We take the denominator. We have a function here that's f, and that function is x divided by x squared minus 9. So we take the denominator, x squared minus 9, and we set it equal to 0. We can factor x squared minus 9 into two different things, which are x minus 1 and x plus 1. Oh, man, rough day. X minus 3 and x plus 3. That's what x squared minus 9 factors into. X minus 3, x plus 3. And then we can take both of those, x minus 3, x plus 3, set them equal to 0 and solve. And we get x equals 3 and x equals minus 3. So you can see that in the graph, I have the graph of function f on the right here. It's broken into 3 segments. The left segment has kind of a bow and arrow that's facing the origin, with the arrow pointing towards the origin, but moved out to the left a bit. So there's a vertical asymptote at x equals minus 3. There's also a vertical asymptote at x equals positive 3. And the function is broken up into these 3 regions: negative infinity to negative 3, negative 3 to positive 3, and positive 3 to positive infinity. And you have an S-shaped curve that goes up to the left and down to the right in the area negative 3 to positive 3. You have kind of an N, or think of a bow and arrow pointing up to the top right in the bottom left corner of the graph. And in the top right corner of the graph, you've got a bow and arrow kind of pointing down. Hopefully this was helpful. If you liked it, subscribe to the channel, give me a like, and thanks for watching.